Let's look at our multiple choice for 6.3 here. Number 1, for which of the following counts would a binomial probability model be reasonable? The number of traffic tickets written by each police officer in a large city during 1 month. B, the number of hearts in a hand of 5 cards dealt from a standard deck of 52 cards that has been thoroughly shuffled. C, the number of sevens in a randomly selected set of 5 digits from a table of random digits. Or D, the number of phone calls received in a 1 hour period, or all of the above. Well, it's definitely not E, because we're going to eliminate some of the others. So if we're looking at binomial, again, we need bins. We need there to be, 2 outcomes, success or failure. We need there to be independent among our selections. We need a fixed number of trials, and we need the probability of success to be constant. Just starting to look at some of these at choice A. The number of traffic tickets written by each police officer in a large city during 1 month. That is not a fixed number of trials. We're not counting, looking at, how many tickets like if they had something like out of 50 tickets written by a police officer, what percent are a certain violation? That might be more binomial. But A is not binomial. B, the number of hearts in a hand of 5 cards. Well, we can stop right there. If you're dealing a hand of 5 cards, that means you're not replacing in between, and so our independence is definitely violated. C, the number of sevens in a randomly selected set of 5 random digits. So first of all, this is different than the card thing. Because when you're selecting random digits, you look at your first digit, and then we would check, is it a 7 or not? So 7 is success, not 7 would be failure. So our binary part is met. Our independence is fine, because when you're looking at a table of random digits, what you get for one digit does not affect what you get for the next digit. So independence is met. The number of trials is fixed, because we're looking at a set of 5. So it would be our N. And the probability of success is constant, because there are 10 digits. One of them is 7, so our probability of success is 1/10. So this one is, C is our correct answer. The reason D is not is, again, we don't have a set number of trials. And really, we don't have success or failure. We're just counting how many phone calls we get. There isn't success or failure. Really, you could say the same thing for A, too. There isn't a success or failure. We're just counting how many traffic tickets they write. But either way, D is not correct. 2, to pass the time, a toll booth collector counts the number of cars that pass through his booth until he encounters a car with multiple bumper stickers. Suppose we define the random variable y to be the number of cars the collector counts until he gets a car with multiple bumper stickers for the first time. Is y a geometric random variable? So now we're checking bins, but instead of N, it's really, sometimes I call it C, excuse me, where we're counting until the first success. But instead of a fixed number of trials, we're counting until the first success. So we can start with that one. Yep, that one's met. We're counting them until we get a car that has multiple bumper stickers. Is it binary? Well, either the car has multiple bumper stickers or not. So check there. We already checked N. Independence. In terms of the cars having bumper stickers, there's no reason to believe that one car, whether it has multiple bumper stickers or not, would affect the next car. So independence should be fine here. The last one's probably the one that throws people off the most, is the probability of success thing. This one is actually fine, simply because of the fact that there is some true percentage of cars that have multiple bumper stickers. We may not know what it is, but that probability of success is constant. It's not going to change as one car goes through, another car goes through. If there are, I don't even know, I'm making numbers, but let's say there's 10,000 cars in some city or town, there is some factual number of the population that has multiple bumper stickers. We usually wouldn't know what it is, but it is a constant probability anytime you're randomly selecting cars from that population. So this is actually A. Now, I would agree most of the time you would know this probability of success, but as long as it stays constant, that condition is actually okay. Number 3, there are 20 multiple choice questions on an exam. each having responses A, B, C, or D. Each question is worth 5 points and only one option per question is correct. Suppose the student guesses the answer to each question, and the guesses from question to question are independent. The distribution of x, which is the number of questions the student gets correct, is what? Well, 4 of the choices are binomial, so if it wasn't binomial, we would definitely go with E. But this is binomial. We have a fixed number of trials. The trials is 20. I don't know why I didn't start with B if I was going to check these, but so it is binary. Either they get it right or wrong. We already told they're independent. There is a fixed number of trials because we have 20 questions, and the probability of success is constant because if they're truly guessing, it's 0.25. If they were taking education guesses, if they knew a little bit and were only guessing, and sometimes they could narrow down to 2 choices or 3 choices, then it wouldn't be a constant probability of success. But for the way this is worded, we're A-okay. So then if we looked at the parameters, in this case we have 20 trials. The 5 points thing is unrelated to anything here. We have 20 questions, and each probability of success is 0.25 because there's 4 choices and only one of them is correct. So B is your correct choice, or correct answer. Number 4, a college basketball player makes 80% of her free throws. Suppose this probability is the same for each free throw she attempts and free throws are independent. If she shoots a series of free throws, what is the probability that her first miss is on the 5th attempt? So when we're looking for the first time something happens, this is setting up to be geometric. The thing that's a little bit weird here is the probability of success is actually the probability she misses, because we are specifically looking for her first miss. So our probability of success is 1 minus the probability she, jumping the gun there. It's 1 minus the probability she makes it, which ends up being 0.2. So then if her first miss is on the 5th attempt, that would be how you'd write it for a geometric variable. But I think that gets to be confusing with the binomial stuff. So maybe we'll just do it in words. Probability that first miss on the 5th shot. That would mean that she failed 4 times, but the probability of failure here is making. She made the first 4, so it's to the 4th power. Then she finally missed, and our probability of, and you can't see me doing the air quotes, but trust me I am, the probability of success is 0.2. So another way to think of it would just be to look at the percentages. Forget about success and failure. You can just think if her first miss is on the 5th, then she made 4, which would be 0.8 to the 4th. Then she missed once on the 5th one. Number 5, a set of 10 cards consists of 5 red cards and 5 black cards. The cards are shuffled thoroughly, and you turn cards over one at a time, beginning with the top card. Let Y be the number of cards you turn over until you observe the first red card. The random variable Y has which of the following probability distributions? A, the normal distribution, with mean 5. Nope, there's nothing here that would suggest normal. B, the binomial distribution with P equals 0.5. Well, we're flipping cards over until we get the first red card, so that's not binomial. C, the geometric distribution with probability of success 0.5. Well, if we check our conditions, is it binary? Yes, either it's red or not. Are trials independent? Ooh, no. We're flipping cards one over one at a time. We only have 10 cards. So as you flip them over, your drawing depends directly on the one before. So we do not have, so this is not geometric. It certainly seems closer to geometric than others, but it is not geometric. Uniform distribution, we're not really going to even tackle. It would be a distribution that is always at a height of 1 from 0 to 1, but you're not going to need to worry about it here. So E is the correct choice. This is just not one of the types of distributions that we analyze. It's a thing. You could answer probability questions with it, but it's not something that we're going to tackle, certainly this section.